Okay, let's now look at a simple example to understand how to classify misses observed for a particular address pattern. So I'm going to design a cache. So let's say this is my 370 cache, X370 cache. It's a cache of size 64 bytes, and it has a block size of 16 bytes, which means that the number of blocks in the cache is 64 divided by 16, so it's 4 blocks. And it's a two-way set associative cache. So what that means is I would take a 16-bit address that is given to be the size of my address, and the block size is 16 bytes, so that means 4 bits are for my block offset. And then it's a two-way set associative cache, so that means the number of sets is going to be the number of blocks or number of lines divided by the number of ways, which is 2. So the number of sets is going to be 2 sets. So to figure out which set I should go to, I just need 1 bit, and the remaining 16 bits is going to be tags. So 16 minus 1 minus 4, so that is 16 minus 5, that is 11. So this is my set index, and this is my tag. So I'm asked to classify this address sequence into the 3 categories that we just spoke about. So remember, I said that in order to classify, first I need to simulate 3 different caches: infinite cache, a fully associative cache, and then the given cache. So let's start with simulating an infinite cache. Now, in the case of an infinite cache, the only restriction that you derive from the problem statement is the size of your block offset. So the block offset or the block size does not change across any of your 3 caches. So the block offset size was 4 bits. The block size was 16 bytes, and so therefore the block offset was 4 bits. So what I have done here is this is a hexadecimal, and so I have partitioned the address into 2 parts, and so this is 4 bits in hexadecimal, so I have kept that separate, and what you're left with here is your tag in your infinite fully associative cache. So the infinite cache is also assumed to be fully associative. It doesn't really matter because you're never going to evict anything out of this infinite cache anyway. All right, so now let's see what cache hits and misses that you will observe in this case. So the first axis, so these are going to be your tags, so I can pretty much ignore my block offset when I'm simulating the cache, right? Because the hit or miss would primarily depend upon the tag and the set index. Block offset has nothing to do with cache hit or miss. So the tag is 0. This is the first time let's say that I have an infinite cache that I can put these tags into. So I'm going to add 0 to my cache. It's going to be a miss, of course, because this is the first time I'm accessing it. So this means this is a compulsory miss. And then I have a block with the tag 1. Again, it's a compulsory miss. Block with the tag 2. Again, it's a compulsory miss. Then block with the tag 0, which we have accessed before. So therefore, this is the hit. Block with the tag 3. First time, compulsory miss. Block with the tag 4. Again, first time, compulsory miss. Block with the tag 1, we already have it in my infinite cache, so it's a hit. Block with tag 2, I do have it in my infinite cache, so it's a hit. Block 0, I do have it in my infinite cache, hit. Block 4, I have it in my infinite cache, so it's a hit. So I have a total of 1, 2, 3, 4, 5. 5 misses and all 5 of these are later going to be classified as compulsory misses, because even in an infinite cache I endured them, and therefore the only way you could have solved it is by increasing the cache block size, but we are not going to do that. Alright, so now let's try to simulate a fully associative cache. So the fully associative cache has 2 restrictions from the problem. So one is the size has to be same as the given problem. So the problem said the cache size is 64 bytes, and we figured out that the number of blocks is 4. So my fully associative cache is going to have 4 blocks, and I'm going to try and simulate my address sequence. And you should assume a replacement policy. I'm going to typically assume a LRU policy for such problems. Now there is a tag array and a data array, which is what we have seen a cache to be architected with, but for such problems the data doesn't really impact whether it is going to be a cache hit or a miss. So it's not really necessary for me to keep track of the tag. In fact, the problems don't even tell me what the data part is. So I can simply ignore this part. I'm going to delete it so that it's clear what I'm simulating, so that it's not cluttered. So the tag is the only thing I care about when it comes to simulating a cache, especially a fully associative cache. Alright, so now I have the tag, and the block offset again doesn't change because it's same as what we had before. Now I have the same set of tags which we used in the infinite cache simulation. So now, because my capacity is finite, I have to keep track of my LRU rank, because it might turn out to be the case that I run out of capacity and I need to evict a cache block, and when I have to evict a cache block, I have to pick the one that is least recently used. So I'm going to keep track of my LRU rank along with the tag that is in the cache. Okay, so my address, I access my address 0, and then that is going to be a miss. Address 1, it's going to be a miss. Sorry, the tag is 2, again it's going to be a miss. Now the LRU ranks would have been, this is my most recently used, and tag 0 is my least recently used tag. So now I'm going to access tag 0 again. It's going to be a hit. So I'm going to update my LRU rank to be 0. I'm going to increment them by 1. I'm accessing address tag 3. It's a miss. Tag 4. Now when I access tag 3, this would have been 0, and these have to be updated. Okay, so now I have to bring in tag 4. It's not there in the cache, it's a miss. I have to evict the LRU, so LRU is going to be 3, so I evict this one, replace it with 4, and set its LRU rank to 0, and increment everyone else's rank by 1. Okay, right, so now I have access to 1. Unfortunately, we just kicked this tag out, so it's going to be a miss. Right, so now I have to kick someone else out to bring in this block. So the LRU is going to be this tag 2. So I'm going to replace this with tag 1 and reset this LRU rank to 0, increment everyone else by 1. Okay, now I have address tag 2. We just kicked it out, so therefore it is again going to be a miss. So I need to find a victim. The victim is going to be the least recently used, which turns out to be this block over here. So I replace this one with address 0, and the rank is going to be 0, increment everyone else's rank by 1. So this is also going to be a miss. And then finally I have access to 4. So in this case I would access the tag and then compare it, and then I will see that it is actually a hit. Okay, so now we finished simulating a fully associative cache, and you'll notice that compared to my infinite cache, I encountered a few more cache misses. So so you'll notice that so now we have finished simulating a fully associative cache. You might have noticed that I encountered a few more misses than I did with my infinite cache. And those cache misses are going to be classified as capacity misses, because the only reason why we encountered those misses is not due to lack of associativity, but really due to lack of capacity. So we'll see which ones are those misses later on, but let's move ahead and simulate the given cache. The given cache, we're calling that as this EX370 cache. So again, I have partitioned the addresses into the block offset and the tag, the block offset and the remaining part. But in this case, I need to compute the set index along with the tag. Because I have two sets, one bit is going to be for set index. So I have to take each one of these, this part of the address, and convert them into tag and set index, where I extract one bit and keep that as a set index. So 0, the last bit, I'm going to write a 3-bit binary number. So 001, 00, sorry, 000, 001, 01. Okay, so now that we have the bits written in binary, so now we have the binary addresses for this part. We can now identify the set index, which is the last bit, and the remaining would be the tag. So we don't really need to worry about the block offset when it comes to cache simulation. So the way that I have represented my cache set is I have the data part. Again, you don't really need to simulate the data. It's only the tags that matter. And I have two cache blocks per set, so I need to keep track of which one is least recently used. Okay, so let's start with the first one. I have the address 0. So the tag is going to be, set index is going to be 0, and it's not there in the cache, so I'm going to store it, mark it as a miss. I'm going to mark the LRU bit with this L bit, so the L bit is the least recently used. Now my next address is set index is 1 and the tag is 0, so again I'm going to repeat my exercise here, mark it as a miss. Then I have a set index 0, tag 1. Unfortunately I have a space here, so I can store my tag here, mark my LRU bit to be the other one, but this is still a miss. Now I have the set index 0 accessing the tag 0, so set index 0, tag 0, it is going to be a hit, and I'm going to update my LRU bit. My next address is 3, 8, and we have set the set index is 1, tag is 1. I don't have it in the cache, so I'm going to move it to the cache. and set my LRU bit accordingly. My next address is 4, set index is 0, tag is 2. It's not there in the cache, so I need to bring it. I need to evict least recently used block in order to do that. So the tag is 2. So this is the least recently used block, so I will replace it with 2 and update my LRU bit to be this. So therefore this is going to be a miss as well. The next address is 1, so this maps to set 1 and tag 0. So set 1 tag 0, it's a hit. I just need to update my LRU bit. Next address is 2, set 0 tag 1, set 0. Unfortunately we don't have the tag because we had evicted it to make space for this tag 2, and so it's going to be a miss. But we need to bring it into the cache, so I'm going to evict this least recently used block and store the new one and update my LRU bit. And my next address is 0, so 0th cache set. I'm going to try and access my tag 0. Unfortunately it's again a miss, and I need to evict my least recently used block and update my LRU bit, and so it's a miss. And the last one, again cache set is 0, and I want to access the tag 2. I don't have it, so it's going to be again a miss. So the LRU bit is going to be updated, the tag is going to be updated with 2. So as you can see, we'll see a bit later when we compile all of these miss sequences together that we encountered a few more misses than we did in the case of a fully associative cache. So those misses are going to be flagged as conflict misses, because the only reason why we encountered a miss in a set associative cache but we didn't encounter in a fully associative cache is because of lack of sufficient associativity. Okay, so what I have done in this table here is I've taken all the results from your cache simulation and tabulated them, and now we are going to go through this table and classify a miss as into one of these 3 types. So the first thing to do is the easiest part, which is to look at the misses encountered in the infinite cache. Now if there is a miss in the infinite cache, that means no amount of associativity or capacity is going to solve the problem for you, because it's a compulsory miss. So any miss in the infinite cache is going to be marked as a compulsory miss. I'm just going to call it as a comp, short for compulsory. So any miss that I see, which is 1, 2, 3, 4, 5, so those are going to be marked as compulsory misses. Okay, so my next step is to go and figure out the set of capacity misses. So capacity miss is one that I encountered in the fully associative cache of the same size as my given cache. Right, so this is my 370 given cache. This is fully associative cache. So I do have 1, 2, 3 extra misses compared to the ones that we have already flagged as compulsory. So this is taken care of, this is taken care of, right? Because these misses have been taken care of because we flagged them as compulsory. So only 3 extra misses remain, and those need to be flagged as capacity misses. Okay, and the final one is to observe any misses that you may have encountered in the given cache which has not yet been flagged. So all of these have been flagged, and except this one, so that has to be classified as a conflict miss. So you'll notice something strange. You'll notice that if you notice this address, it turned out that it was a hit in the set associative cache, my given cache, but it was actually a miss in the fully associative cache. Now this strange phenomena happens once in a while, illustrating the fact that a set associative cache can actually have lower cache misses than a fully associative cache. Now the reason for this dynamics is because of the replacement policy not being perfect, right? So for the fully associative cache, we used the least recently used policy, and we know that it's just a heuristic, it's not meant to be perfect. And so it so happens that the set associative cache accidentally, or rather luckily, separated out conflicting cache blocks and managed to turn this particular access into a hit. So that can happen. And keep in mind that our goal is to really classify the misses in the given cache into these three types. And so given the fact that this one is actually a hit and not a miss, we don't really care about this. So this is not applicable. And this one is also a hit, so therefore that's not applicable. So our end goal is to classify the misses in the given cache into one of these three types. And the reason why we simulated these two is so that we can classify these misses into one of these three types. Okay.